We previously saw in order to regenerate the message signal from the VSB modulated signal or for the demodulation of the VSB modulated signal, it was essential that the sideband shaping filter to demodulate the VSB modulated signal maintains the condition h of f plus fc plus h of f minus fc is equal to 1, or the frequency f lies between minus w to plus w. Here, HF is the transfer function of the VSB sideband shaping filter. Now we will understand this VSB sideband shaping filter in details. The sideband shaping filter plays an important role in the generation of the VSB modulated signal, which transmits one sideband along with the vestige of the another. This VSB modulated signal has two parts: main sideband with a portion of its spectral missing, in this case it is the upper sideband, and the vestige of the another sideband, in this case it is the lower sideband. The condition to generate VSB modulated signal is that the sideband shaping filter must have a frequency response such that the vestige of the sideband or the lower sideband in this case must compensate the missing portion of the main sideband during the sideband shaping operation. This requirement ensures that during the demodulation of the VSB modulated signal, we can retrieve the original message signal almost as it was before the modulation. Although the demodulation method preserves the same shape of the message signal, but the message signal is scaled by a factor of AC square by 2. According to the previous lecture, the frequency response of the demodulated message signal can be given by Z of f is equal to AC square by 2 into h of f minus fc plus h of f plus fc into m of f. And after performing the demodulation, a message signal will be obtained scaled by a factor of AC square by 2. And for this demodulation, the frequency response of the sideband shaping filter must be satisfied with the condition h of f plus fc plus h of f minus fc equal to 1, where the frequency f lies between minus w to plus w. Here, fc is the carrier frequency and hf is the transfer function of the VSB sideband shaping filter. If the condition is maintained, then from the equation of the z of f, the demodulated signal will become AC square by 2 into m of f, which is the frequency response of the message signal multiplied by a constant AC square by 2. Now, this frequency response of the VSB sideband shaping filter looks like this, and the term h of f minus fc, which is the positive frequency part of the bandpass transfer function, can be obtained by shifting hf by the frequency fc, and the term h of f plus fc, which is the negative frequency part of the bandpass transfer function, can be obtained by shifting the frequency hf to the left by the frequency fc. By adding these two terms, we will obtain h of f minus fc plus h of f plus fc. Let's see some properties of this sideband shaping filter. First property is that the transfer function of this sideband shaping filter must exhibit an odd symmetry about the carrier frequency fc. To understand this property, let's define hv of f, which is a new low pass transfer function and it depends on the vestige of the modulated signal, and u of f, which is the unit step frequency function. Then we can represent the transfer function of the VSB sideband shaping filter h of f as h of f is equal to u of f minus fc minus hv of f minus fc for the frequency fc minus fb to frequency fc plus w. Here, u of f minus fc is the unit step frequency function u of f shifted by the frequency fc, and hv of f minus fc is the new low pass transfer function hv of f shifted by the frequency fc, and this is completely determined by the vestige of the modulated signal. Again, h of f is equal to u of f minus fc minus hv of f minus fc, and this transfer function h of f is band limited between the frequency fc minus fb and fc plus w, where fc minus fb is the lower frequency component and fc plus w is the higher frequency component. That's why the transmission bandwidth is the difference between the higher frequency fc plus w and the lower frequency fc minus fb, which is equal to fb plus w. Let's talk about this shifted unit step function. The original unit step frequency function or u of f has the value of 1 when the frequency is greater than 0, and for this unit step frequency function of u of f minus fc, we need to shift the original unit step frequency function by the frequency fc, and then this shifted unit step frequency function will have the value u of f minus fc will be equal to 1 when the frequency f is greater than fc, and it will be equal to 0 when the frequency f is less than fc. This shifted unit step frequency function is the first term of the transfer function h of f. Let's talk about this new low pass transfer function or hv of f minus fc. According to the property 1, the transfer function hf displays an odd symmetry, and this odd symmetry completely depends on this low pass transfer function or hv of f minus fc. hv of f minus fc depends on the odd symmetry transfer function represented by hv of f, and that will help us to determine the vestige part of the VSB signal. At first, we will find the inverse this function hv of f, which is minus hv of f, and this also represent an odd symmetry function with the negative amplitude. Next, we will determine minus hv of f minus fc by shifting the signal minus hv of f to the right by the frequency fc. And this minus hv of f minus fc exists from fc minus fv to the frequency function fc plus fv, and the center frequency is fc, and it displays odd symmetry. Though this function minus hv of f minus fc is an odd symmetry function which exhibits odd symmetry about the center frequency. Now we have determined both u of f minus fc and minus hv of f minus fc. From these two, we can obtain the transfer function h of f of the sideband shaping filter. According to the condition of hf, these two terms or u of f minus fc and minus hv of f minus fc needs to be added together in the frequency domain to find h of f. For the frequency minus infinity to fc minus fv, both of the signal has the value 0, so the value of the transfer function or h of f equal to 0. For the frequency fc minus fv to the frequency fc, the value of shifted unit step transfer function is 0. And if we put this value in the equation of h of f, then h of f will completely depend on minus hv of f minus fc for this frequency range. When the frequency f is equal to fc, then the value of shifted unit step transfer function is equal to 1. By putting this value in the equation of hf, the value of the main transfer function hf will be 1 minus hv of f minus fc. Or for the frequency f less than fc plus fv, we will just add the value 1 with the value of minus hv of f minus fc. At the frequency fc plus fv, again shifted unit step transfer function is equal to 1, but minus hv of f minus fc equal to 0. So the h of f will have the value u of f minus fc, or which will be equal to 1. For all the instant from fc plus fv, the transfer function hf has the value 1, but this transfer function is band limited to the frequency fc plus w. So this is the specially designed sideband filter for the generation of the VSB signal, which is band limited to fc plus w. And we can also see that here hv of f satisfies the property of odd symmetry about the zero frequency because it maintains the condition hv of minus f equal to minus hv of f. As hv of f maintains the odd symmetry at zero frequency, so we can say that the shifted low pass transfer function or minus hv of f minus fc will also maintain the property of odd symmetry at the carrier frequency. Now, as this minus hv of f minus fc is included in the representation of the transfer function h of f, and the minus hv of f minus fc maintains the odd symmetry of the carrier frequency fc, we can say that our transfer function of the sideband shaping filter or h of f will also exhibit odd symmetry about the carrier frequency. Now, next property is that the transfer function h of f required to satisfy the condition f of f plus fc plus f of f minus fc equal to 1 for the frequency interval minus w to w, where w is the bandwidth of the message signal. We have seen the representation of h of f as shifted unit step function u of f minus fc and minus the Laplace transfer function minus hv of f minus fc. This transfer function has the value of 1 when the frequency is greater than or equal to fc plus fv, and this will continue to infinity as the shifted unit step function or u of f minus fc continues to infinity. Then this filter will be impossible to design. That's why it needs to be band limited to a certain frequency, and that frequency is fc plus w, and it is the reason that the spectrum lying above fc plus w is shown dashed. So by limiting this transfer function of the sideband shaping filter or h of f to the frequency fc plus w, it also maintains the second property. So we can say that h of f plus fc and h of f minus fc will be equal to 1 for the frequency interval minus w to plus w. This concludes our discussion for this lecture. In the event that you have any question regarding this presentation, feel free to post them in the comment section, and don't forget to hit the subscribe button. See you in the next one.